Here's another geometric type optimization problem for us to work with. Step 1, go ahead and read through the problem to make sure you understand what we're building. Let's determine the objective. We're asked to find the volume of the largest box that can be made, so we are maximizing volume. And now we want to draw a picture. So this one might seem a little abstract, and drawing this picture of the process of making this box will help us understand it much. So it says an open top box is to be made from a square sheet of metal 12 inches on each side. Let's just stop there and draw that out. So there's my square sheet of metal, and they say it's 12 inches on each side. So 12 inches there, 12 inches there. The next piece of that sentence says we'll make this box by cutting a square from each corner and folding up the sides. So we're going to cut a square from each corner. So there the red dotted line indicates the squares that I'm cutting from each corner. So there I've redrawn the shape with the squares cut out of each corner. It then says we'll fold up the sides. So imagine folding on this black dotted line. We would fold up each side and it would make a shape kind of like that on the right, like a shallow tray. Remember, it's open top box, so there's no lid on it. We can see inside it. So that's what we're making. Let's go ahead and think about the objective function in step 2, right? We're creating a volume function because we're maximizing volume. Volume, recall, equals length times width times height. So my volume function that I'll create will be made of these 3 components here. I don't know any of these components though. I don't know the length. I know it starts out as 12 inches across, but then we cut out these squares of each corner. Same thing with width. It starts off at 12, but then we cut out those corners. Remember that if there's a piece of information we don't know or changes, an unknown, that is our variable. So the length of each side of these squares that we cut out is our variable x. So we will let x be the length of the side of the square cut from each corner. And since they're squares, every side of each red box there will be x all the way around. Now let's go back to our function and think about just one component, the length. How long will this shape be based off my picture? Well, it starts out at 12 inches, but then I'm cutting out 2x inches from the side. So I'll minus out 2x. The width also starts off at 12 inches, but then I cut out 2 x's. 2x inches. The height, imagine this shape now being folded up, and let's focus on the shape on the right. How high is that shape? It is x units high. I realize I'm not the best artist, and my lines aren't that straight, so here's a more professional picture from the textbook so that you can better understand the shape of what we're making and how we gathered that formula. So here's the materials we started with, and we cut out x inches from each corner, and then we fold it up to make a shape like this. So we've finished step 2. We've created the function that we're going to optimize since we're maximizing volume. But first, let's go ahead and distribute all these pieces in and simplify it. So there I just foiled both of those quantities of the 12 minus 2x together, and I'll further multiply in the x on the outside to all 3 terms in the parentheses. Great. This will be a much simpler derivative in step 3 since we've done this. So step 3 is to find the critical numbers of this, which is a simple process of taking the derivative, setting it equal to 0, and solving for x. There's my derivative. Let's set it equal to 0 and solve for x. The greatest common factor here is a 12, so let's factor that out. And I also rearrange the term so the x squared is up front. It'll make factoring this, I think, a little easier to see. So we're finding 2 numbers that multiply together to positive 12 and add together to minus 8. And those answers are minus 2, minus 6. So the solutions for this problem, or the critical numbers, where the derivative is equal to 0, are 2 and 6. Let's remember what x is equal to. X is the length of the side of the square cut from each corner. One of our solutions was 6. Imagine what happens if we cut 6 inches from each side, we essentially will destroy our piece of metal. We'll cut it straight in half. Or mathematically speaking, 6 is outside the domain of the function, so we cannot use 6. Therefore 2 is the critical value that we'll move forward with. Step 4 is use the critical number to answer the question parts. There's only one question part. It says find the volume of the largest box that can be made in this way. So we're going to calculate the volume. The length times the width times the height. Here is our volume equation. Let's go ahead and plug 2 into the function to calculate that max volume. And we get an answer of 128 inches cubed.